Assalamualaikum warahmatullahi wabarakatuh, and good day to all students. So now let's look at the next examples, which is typical connection examples, and this example has been uploaded as well in our Google Classrooms. Alright, so for as has been explained in the theory session, where the main beam to column connections in most of the steel structures is considered under typical connections, which means it will consist of variety types of connections, and among of it you can have like what you can see in this figure. As you can see in this slide, okay, you can see there are many types of typical connections, which consists of, as you can see in this figure, where you can have a bolted pin connections. As shown in figure A, you can have pin joint tie rod connections, and B, you can have beam to column connections with angle sections at the top flange and the bottom flange, where in these types of connection the beam to column will experience shear force and the tie force. And if you look at figure C, you can have a short call of what we have pin connection or fin plate connections. Also for bolted pin connections, you can have shear force and tie force acting together. And D is showing the beam to column connections, where you have the angle sections connected the beam to the column, and the secondary, this usually happen for secondary beams. Meanwhile, you can also have a welded bolted pin connections, which this also considered as typical connection examples, where you can see in E, beam to column connections, where the plate is welded to the beam and the beam also is bolted to the column. And F, you can see the plate welded to the column, and in this case you will have the shear force and tie force together. And G is the beam to column, plate welded to end of beam, where this is always happen to secondary beam connections. And you have the column to foundation, where you have the base plate welded to columns. So here are all the examples of typical connections, but for the sake of examples, I'm not going to show or explain into detail every types of the connections, because they are all using the same concept. So therefore, in these examples, okay, I choose one of it, which is the we consider as typical connections. Okay, so I will explain based on these examples, and the rest of the examples will be given in soft copy mode, where you can download and refer to the how to design another types of typical connections. Okay, without further ado, let's look at our first examples for typical connections. So if you look at these typical connection examples, you can see that in these examples here, this is the column, okay, this is the column, and this is the beam, where the beam is bolted to the column flange, where you can see there are 3 rows of bolted connections, okay, and there are 2 sides, which means you have this side and the other back side. Okay, so 2 rows, 2 columns of the 3 rows bolted connection. And here, okay, here where you can see the outer line here is the end plate with 6M24 class 8.8 bolts, Alright, and the beam is UB457191 kg per meter. The distance from the center of the bolt to the bottom flange is 50 mm, and similar here, and the center distance between bolt to bolt at the upper side of the flange is 110 millimeter. And here what you can see is the more like what we call as the stiffener of the panel zone. Alright, so for you to analyze these examples, okay, because we didn't usually for an engineer you will not be dictate, or you will not be given any sort of order for you to check. No one will tell you, okay, you need to check the resistance of the bolt due to shear. You need to check the resistance of the web due to shear, for instance, or you need to check the shear resistance of the plate and plate. So basically no one will tell you about what to check for the connection design. Therefore, for this connection design, okay, or for every typical connection design, you need to understand what are the sort of failure mechanism that will occur for a particular connection design. As you can see in this figure, maybe you can think what sort of failure mechanism that will happen in this particular set of connections. Because in these questions, the question just asks you to determine whether the given proposed connections is sufficient to carry the loads or not. And assuming that we have calculate the transfer load to these particular connections, where the shear that will carry by the connections is 100 kilonewton, while the moment that we're acting to this particular connection is 200 kilonewton meter. Okay, before we start these verifications, okay, I would like you guys to illustrate or to predict what are the sort of failure mechanism that will happen for these particular connections, because the failure mechanism that going to exist, that must be verified to make sure that the connection system able to resist all those failure mechanisms. So when you look at these examples, of course, first thing what you need to do is to check, okay, is to check the positioning of the bolt holes. Okay, refer to the tables and check whether the distance of the bolt holes and everything are they satisfied and within the allowable limit given in the Eurocode tables. Okay, and what is the next failure mechanisms? Of course, once you have these bolt connections and then you get shear here, okay, definitely the bolt, all these bolt will need to resist the shear that cross through this plate. Okay, so definitely the bolt will be in shear, and at the same time the bolt also will be in tension why the bolt will be in tension. Some of the bolt will be in tension, some of the bolt will be in compression. Okay, but definitely there will be in tension at this particular point, because when you have this moment, okay, when this moment pull rotate, okay, let's say imagine this is your bolt, okay, this is your bolt, and then there is a moment at this particular directions. So this moment will cause the bolt to twist, okay, will cause the bolt to twist, okay, to twist down here. So when the bolt is twisting together with the moment, so the bolt definitely will acting in tension. This will be in tension. Okay, so second mechanism is bolt in tension. First mechanism is bolt in shear. Second mechanism is bolt in tension. Okay, and another thing, when the bolt is experiencing shear, definitely each of the bolts will need to be checked for bearing resistance as well. And you also need to check, okay, since in these examples the end plate is welded to the column, sorry, the end plate is welded to the beam, so therefore the shear resistance of the welded, okay, which is welded to the beam, must be checked as well. And then the resistance of the end plate due to shear also must be checked, which if you need to check whether the shear will cause the block tearing of the end plate or not. Alright, and definitely in these examples the combinations of shear and tensions of the bolt must be checked. To list the mechanisms, okay, here are the things that you need to check, which is the first one, positioning of bolt holes, whether it is within the allowable limit or not, bolt under shear, bolt in tension, and also a combinations of combination, actually you need to check for the combinations of bolt in shear and tension, and then bolt in bearing, resistance of the welded connection between the beam and end plate connections, and then you need to check for the end plate in shear, web of the beam in shear, block tearing of the bolt split. Okay, so basically these are the failure mechanism that we expect to trigger in these particular examples. However, because of the sake of the examples, in these examples how to check the positioning of bolts will not be shown in these examples, as it has been shown many times in other examples. And bolt in bearing also will not be shown, because it has been shown in the other examples as well. And the resistance of welded connections also has been explained in other examples. So end plate in shear, web, this one is also in the examples. Block tearings also has been explained in the previous examples. So only the combinations of bolt and acting in shear and tension, which is combinations, has not been shown in any other examples. So for these examples I will only show how does you need to check the verifications bolt under combined shear and tensions, because the rest of the other failure mechanisms have been shown in other examples, and the concept is there. It's just that you need to apply for a particular connection that you are doing at the moment. Okay, to do this, first of all we need to know what or we need to determine how much the shear forces that need to be carried for each bolt. So in these examples, what you can see, we have 3 rows of bolts, 1, 2 and 3, and then these bolts actually they are in both sides. Where what does it mean in both sides? If you look from the in front, okay, let's look from the in front. So here, connections. So here are the end plates. Here is the beam. Okay, the beams, and then you have bolts. Okay, there are 2 sides, so one here, one there, and then you have another one here, one there, and here you have one here, one there. So here basically is the column. Okay, so here is the columns. This is when you look from this side. So this is your beam, and this is the end plate, which is where the beam is welded to the end plate and the end plate is bolted to the column. So if you look here, okay, there are 1, 2, 3 rows of bolts at both sides, and because of it, you have the shear, which is 100 kilonewton. So the shear is 100 kilonewton. So this shear, we need to determine what is the shear that will be carried by each bolt when you have altogether 100 kilonewton. So what you need to do, this 100 kilonewton, okay, must be divided by 6. Why 6? Because you have 1, 2, 3, 4, 5, 6. 6 numbers of bolts. Okay, so each bolt, meaning that one bolt, okay, one bolt, the capacity is 16.67 kilonewton. So this must be able to carry 16.67. This also must be able to carry 16.67, and similarly goes to another bolts. Okay, so that is how you determine the actual capacity or the load that is need to be resisted by each bolt. So now, how about the tension side? Because as I said earlier, when you have moment, so when this moment causes the beam to twist, definitely it will pull the bolts. Okay, when it pulls the bolts during the rotations, the bolt will definitely under tensions. So you need to determine what is the tension force. Okay, what is the tension force acting at each of these bolts? So to determine the tension force, okay, you can look at this figure. Okay, tension per bolt, assume rotation about the center of the bottom flange. So this is your top flange, this is your bottom flange. You are assuming that the rotation due to moment will acting at the center, which means this, at the center of the bottom flange. So, and then the total depth from 0 to the top of bolt, so meaning that this is 0. So you need to determine, because you have one bolt here, so this is your first bolt, T3, and then you have second bolt, T2, and you have T1. So the distance need to be calculated, whereby from the center to the first bolt, from the center to the second bolt, from the center to the top bolt. So we define it as the distance from the center of the bottom flange, okay, to the first row of bolt is D1, center to the second row of bolt is D2, center to the third row of bolt is D3. So here are the way how we're going to calculate the tension force, and this is the thickness of the flange. Okay, and here is D is the total height, where you can get it from the section properties for UB 457 19667 for D. Okay, so here you referring to the diagram that we have earlier. Okay, I hope you have sketched them. So we can now calculate D1. D1 is equivalent to D minus T over 2 plus 50. Why T over 2? T is the thickness of the bottom flange, because we measured from the center. If you look here, we measured from the center of the bottom flange, so therefore T must be divided by 2 plus 50. Okay, so therefore D, the total height of the beam, must minus the thickness of flange divided by 2 plus 50. So this one you can get from the section properties for UB section, minus 12.7 over 2 plus 50 mm, which is, this is the distance of the bolts, okay, from the top flange. And then you get D1 is 497.25. And similarly you can calculate for D2, D3. Okay, so D2 is here. Okay, and then you know that the distance between T1 and T2 is 110 millimeter. So the overall height D1 minus with 110, you get 387.25. And D3, you know it is 50 mm. Okay, the distance from the center to the base of the top of the flange for the bottom flange is 50 mm, as you can see here, 50 mm, plus with T over 2. Okay, because it is from the center of the bottom flange, T over 2. That's why you have 56.35 millimeter. So in that case, for you to get what is the tension, okay, what is the tension, because the objective now is we wanted to know what is the tension force acting for each of these bolts. Okay, we wanted to know what is the tension force acting for each of these bolts, because for the shear force we already calculate. Now we wanted to know what is the tension force. So you need to take moment about 0. Okay, this we take moment about the origin 0, which is at the center of the bottom flange. Okay, and where you can get is something like this. Okay, where submission moment at origin 0, and then you can have T1 minus the level T1 times with the lever arm D1 plus T2 times with the lever arm D2 plus T3 D3 minus M. But T2 equivalent to D2 over D1 T1, and T3 we can assume that equivalent to D3 over D1 T1. This is the assumptions that we can use in order for us to get what is the T1. So thus in this equation we can have, like, in terms of the T2 and T3, so we can get M equivalent to T1 over D1. Okay, and then you have D1 squared plus D2 squared plus D3 squared equivalent to these simplifications of the formulations. And when you rearrange these formulations, you can have whereby T1 equivalent to M, which is the moment, times with your D max divided by summations of I1 to N D distance I squared. Okay, so then you can calculate what is your T1. So here you can calculate what is your T1. Okay, so you know the distance, you add them up, the distance. Okay, the distance D1, D2 and D3 from the previous calculation, D1, D2 and D3 from these calculations. So you insert in the equations. Okay, insert into the equations. So here you get D1, D2 and D3 times 2 rows of bolts. Okay, times 2 rows of bolt, because you have 2 times, so therefore you get 801 times 10 to the power of 3. In here you get T1 is 124 kilonewton. So the tension force is 124 kilonewton. So once you get your T1 equivalent to 124 kilonewton, so then you can find what is your T2 and T3. Earlier we have defined that, okay, T2 is equivalent to D2 over D1 T1. So you just insert D2, which is 387.25, over D1, which is 497.25, times with T1, which is 124, you will get what your T2. Similar, go for T3, just insert the distance D3 and D1 times with 124, which is T1, and then you will get what is your tension for T3. So in these examples, I will show you how you can check the verifications of the combinations tension and shear for the first bolt, which is this bolt. Okay, for this bolt. Okay, referring to the slide, okay, if you can see at this slide, there is a failure mechanism that must be checked under the combinations of tension and shear combinations. So those combinations, okay, if you look here in this table, combined shear and tension is given by equations whereby FVED over FVRD plus FTED over 1.4 FTRD, and it must be lesser than 1. The total resistance must be lesser than 1. Okay, and also you can see here the tension resistance alone, which means the tension resistance that need to be carried by the bolt, which is FTRD, K2 FUB AS over gamma M2. So in these examples, the resistance of the bolt must be checked at the conditions where it resists the shear alone, which is the resistance of the FVRD, and then the tension resistance alone, which is FTRD, and the resistance of the bolt under the combinations of tension and shear resistance. Okay, so for now, let's first check the resistance of the top bolt. Okay, the top bolt, which is this bolt. Okay, this bolt and this bolt under tension, under shear, and how does the resistance of this bolt under tension and shear, which is combinations. Let's look one by one. Let's first look at the shear resistance per bolt. So shear resistance given in the equations is these equations, and alpha V is equals to 0.6 because our bolt is categorized under 8.8 rate, and the alpha V has been given as 0.6, and then the FUB is 800, area of bolt is 353, which is taken from the table, and you calculate all, you get 135, which is larger than 16.6, meaning that one bolt, okay, the resistance of one bolt is 135.6 kilonewton if based on the capacity, and the actual load that apply to that bolt that has been calculated earlier is 16.67. So therefore the load that been applied to the bolt is much lower compared to the resistance of the bolt that it can carry. Therefore it's okay. And next check is to check the tension resistance per bolt. Where tension resistance per bolt, you have FTRD, and this equation refer to the table where you need to find K2 FUBAS, and K2 is given as 0.9, okay, as given in the tables, the factor, and 800 353 similarly you can get from the information of the tables based on what are the criteria of your bolts and so on. And then you get to O3, which is the tension T1 that we calculate is 124. Okay, so 124 is for the top bolts, and then when you calculate the resistance for the top bolt is 203. Therefore in this type of connections, the top bolt is still able to resist the 124 kilonewton because the limit is 203. And as I said, for each bolt you need to check for the shear resistance, tension resistance, and at the same time you also need to check when the bolt is under combined shear and tension, and they must be lesser than 1. So you have your FVED, FVRD plus FTED over 1.4 FTRD. This is given in the tables. So substitute all the equations. Okay, substitute all the equations. 16.67 is the design shear force over the resistance shear force plus design tensile force for the bolt at top divided by the 1.4 times with the resistance tensile force for the bolt, and when you calculate you get 0.56, which is less than 1, and it considered okay. So what I'm trying to say here in these examples, okay, in these examples, the top bolt is satisfactory in carrying the shear, also satisfactory in carrying the tension alone, and when we check whether the bolt is still able to carry the combination of shear and tension, yes, the bolt pass those check. The examples only shows for the top bolt, but definitely you must to complete these examples by checking through for the next row of the bolt, which is this second bolt and the bottom's bolt, the third bolt. And also definitely, as I mentioned earlier, there are many other failure mechanisms that must be verified, but these examples, because I haven't shown any examples with the combinations of bolt and shear, the combinations of bolt under shear and tension, therefore in these examples I only explain how you can check the resistance of the bolts under shear and tension. However, the rest of these mechanisms, which is bolt in bearing, welded resistance of the welded connections, end plate in shear, web of the beam in shear, and block tearing of the bolt end plates, so definitely all this must be checked as well to complete. And once you complete checking all these examples, okay, when you have complete checking all these failure mechanisms and ensure that all of them are satisfied per Eurocode, and then you just can conclude whereby whether this connection is sufficient or not. Only can be you can only conclude once you have checked the rest of these failure mechanisms. Okay, so your task is to check the rest of the failure mechanisms because we have done those previously. Any assumptions in terms of the bolts arrangement you can assume at these examples for the sake of the examples. Okay, thank you. Let's look at the other examples.